Okay, so today and tomorrow we're going to talk about exponential function context and data modeling. So we saw this last unit, like towards the end when we kind of did it all together. In this unit, we've talked about exponential functions. Now let's talk about modeling. So we will construct models for different situations involving proportional output values because we know that's what characterizes an exponential function. And this is a key part. Apply exponential models to answer questions about the data set or the story problem. Okay? So some of our things that we've already known up to this point is that our general form is f of x equals ab to the x. A story problem, it's the initial value wherever we're starting, that y-intercept. If b is between 0 and 1, it's decay. If it's bigger than 1, it's growing. And its property is it's got a constant proportionality. Now, as we learn rules and patterns, there's oftentimes small exceptions. So let's talk about a small exception first. Sometimes data from an exponential function does not display exponential growth, but this is because of a vertical translation. Because what we can do is we can take an exponential function and we can add or subtract a value from it. It's still exponential, but the table doesn't look exponential. Okay, so that's what we're going to do in this first example. We kind of hinted at this a little bit back in like topic 3. So selected values from several exponential functions are given in tables below. For each, find the constant value that can be added or subtracted to the output values to reveal a proportional growth pattern. Then write the equation for the model. So these are good non-calculator questions that you could see in something that would be multiple choice. Okay, so let's look at f of x. So f of x is going from 7 to 13 to 25 to 49 to 97. Now, as we take a look at these pattern of numbers, we know that going from 7 to 13 to 25, there's not something that we can multiply by the same number to get a constant proportion. Okay, but what would be some numbers here that look like that could be multiplying by the same number? Go ahead.
Can I say what I saw?
Yeah.
So 7 after 13 is 6. 13 to 25 is 12.
Yes, there's no pattern there.
Oh.
Yep.
Oh.
Doesn't
it like double each time? Like
it looks like it almost does.
It's close to doubling.
It's close to doubling.
Because 25 to 29 is 24.
It's almost. So
it's like times 2 minus 1.
So we do see kind of maybe a little bit of a doubling feature here. But what if we change 7 to a number and 13 to a number that would represent a doubling? What do you think we would do? Go ahead.
Subtract 1.
Subtract 1. Because if we subtract 1 from all of those y values, I get 6, 12, 24, 48, and 96, which then is truly doubling. Okay. Now, let's write the function. So, this is f of x. As I look at my table, what is my beginning value?
6.
Oh, no, sorry, for f.
Oh,
7. It is 7. What is that constant of proportionality?
-1.
We'll get to that in a second. Over here, what's happening with these numbers?
Times 2.
Now, this is where that -1 comes into play. This table right now does not represent the pattern. Wait, hold on 1 second. not 7, it's 6. I'll tell you why in a second. When we do 6, it's almost like we're looking for kind of the parent function, the foundation. So if we do 6 times 2 raised to 0 plus 1, that's how we get 7. If we do 6 times 2 raised to the first, that's 12 plus 1, that's 13. If we do 6 times 2 raised to the third, that is 24 plus 1 gives me 25. So where I see the operation to get to the pattern, I do the opposite in the actual equation. Okay, so I see a -1, that changes to a +1. Now let's look at this one, g of x.
I think I got it.
What do you think it is?
Multiplied by 3 minus 4.
So like adding 4?
Oh, because like 2 times. Yeah, adding 4. That's what I meant.
So if we add, so let's see. If we added 4, that would be 6. Adding 4 would be, adding 4 would be 14. Well, it's okay. Sometimes it does take the guess and check. Sometimes it does. Let's see. We do see it's growing, so we know that the b will be bigger than 1. If I wouldn't see this necessarily like the 2 needing to become negative. If we did 1, if we did 2, check this out.
Yeah, then
2
times 3.
4, 12, 36, 108, 324. So where here we saw times 2, times 2, times 2, times 2. Here we see times 3, times 3, times 3, times 3.
What's the said Siri? Times 3. Times 3. Siri.
You can't.
Sorry.
Well, they said sorry. That's fine.
All right, so this function is 4 times 3 raised to the x minus 2. And how about this last one? So this last one is decaying.
Wait, is it minus or plus 2?
It is minus 2 because it's the opposite of what we do up here.
Gotcha.
Because basically what we're doing is it's a little bit of an equation. Whereas like I know the pattern is 4 times 3 raised to the x. But then to get these values here, I have to add 2. So to get to these values, I subtract it. Yep. All right, how about this next one? We got 63, 31, 15, 7, then 3.
It's decreasing.
It is decreasing, so that b is going to be between 0 and 1. Go ahead.
Is it plus 1?
Plus 1. It is plus 1. Doing that is the hardest piece of these problems.
Yeah. The rest of it's kind of just similar to what we've already done.
Yep. So the values are 4, 8, 16, 32, and 64. Okay. So that is cutting in half. Times 1/2. Times 1/2. Times 1/2. I do want to just encourage you to be thinking about these transformations, or not. I do want you to think about this more in terms of multiplying by 1/2 rather than dividing by 2, because we do back earlier on, we talked about how exponential functions is based on multiplying. Um, so this is 64 times 1/2 raised to the x minus 1. I think this is the hardest example.
Example 2.
No, example 1. No, from here on out, well, I feel it's more straightforward. All right, so next problem. We're going to find an exponential model in the form of ab raised to the x without the calculator. Then we're going to find f of -1. So here's something pretty cool. So these problems, our main idea behind these is that when we go from 2 to 4 to 6 to 8, it's being multiplied by an equivalent proportion, right? But here we see it's skipping, right? There are two different ways that we could do this. We could do this like our geometric sequences. Let me show you another one. When I think of f of 4, I'm told that f of 4 is 162, right? Which, if I filled out that expression, it's a b raised to the 4th, right?
Yes.
Then, if I take f of 2, which is 18, this is ab squared. Now, I could have picked any of the other ones too. We have said that as we move from one term to the next, whether we're talking about a geometric sequence or an exponential function, there is that common ratio, right? As we move from one step to the next. So does that mean that if we went from 2 to 4, 4 to 6, 6 to 8, that there would be even a proportion there? No. And this is where, like, unless I've had been told, I've had to have been, like, this is what am I trying to say? There's just sometimes in math when it's like, how can we use these different expressions? That there are some things that come to light that are pretty self-explanatory. There are some things that aren't self-explanatory. This one is kind of in the middle. These are proportional, right? Because they're proportional, we can think about the ratios between one term and a term down the line. So if we're trying to find what the a and the b are, okay, we're doing this without the calculator, I can use a ratio to calculate some of these different parts. Okay. For instance, 162 divided by 18 is 9. What is a divided by a?
1.
What's b to the 4th divided by b squared? B is 3, right? Square root of 9 is 3. In a scenario like this, I would not be considering positive or negative 3 because I know this is an exponential function. B cannot be negative. Well, if I know b is 3, I can figure out what a is. 18 equals a times 3 squared. 3 squared is 9. What's 18 divided by 9?
2.
My function is 2 times 3 raised to the x. F of -1 is 2. 2 times negative is 2 times 3 raised to the negative 1, which is 2/3.
Mr. O, for that 18, is that 3?
Yes.
A 3 squared? Okay, this one.
Yeah. Yep. Yeah, sometimes when I write it on, it doesn't like smooth it out entirely.
Okay.
Yes, we could have also done this in the calculator. Alright. Example 3. Alright. For 0 to 10 minutes, water is poured into a container. The height of the water in inches can be modeled by an exponential function. After 2 minutes, there is 3 inches of water. At 8 minutes, there is 7 inches. Write 2 equations that can be used to find the values for A and B. Okay. So, if I know that there are 2 minutes, after 2 minutes, there are 3 inches of water, what is, if I have this model here, how could I write, if I have this sentence here, how could I plug this information into my equation? What could I do?
H of t equals a 3 raised to the 2.
You're close. So if t is 2 minutes, right, it'd be h of 2. What is the height at 2 minutes?
3 inches.
So that's 3 inches. H of 8 is 7. Oh, sorry. We could solve this, but it'd just be like what we just did. Here is why this is here. You have 2 equations and how many variables?
2.
When we talk about 2 equations with 2 variables, what are we talking about?
System of equations.
A system of equations. One thing that you're going to need to learn how to do is in a story problem is when you have data points, you need to be able to write a system. You did that on your test with that polynomial, with that quadratic. You had 3 lines. You can do it with exponentials as well. Okay. If this is probably a simpler version, but if you had a prompt like this on the AP exam and you did that, 1 point. Just for writing 2 equations. Then we could go and use the calculator and find what the A and the B are. Example 4. A population of bacteria in a petri dish starts at 20 bacteria. Every 4 hours, the population, I'm guessing it says it increases, grows at 5%. Find a model representing the population and then determine the population at 18 hours. All right, so this is one of the applications you could see in a multiple choice type of question. So we are starting with f of x is a b to the x. What is the a in this scenario? What's the a?
5%.
No, remember
No,
a is the beginning value.
Sorry. I guess it'd be 20, right?
Good.
20.
Now, it says that this is growing at 5%. When we are doing that, what do I have to do with that 5%? Go ahead.
You multiply it. You multiply the 20 by 0.05.
Ooh, no.
No.
What'd you say? I thought I heard.
No, I was feeling the wind.
Oh. What do we have to do to that 5% so it represents growth?
Divide it by 100 at 1.
No.
Dang it.
Wait. Yes. 1.05. So we take that 5%, make it the decimal, we add the 1 because it says growth. It's growing at 5%. Okay? If it said decaying at 5%, we would do 1 minus 5%. Okay? That's like what happens when we do things that are on sale. Now the exponent. The exponent is a very important piece. It says that this is growing at this rate every 4 hours. What? I'm going to give you 2 options. I'm going to write them over here. Do you think we'll do 4x or x divided by 4?
X divided by 4.
It is x divided by 4 because we're saying once it reaches the 4 hours, then it's being multiplied by this rate. Okay? F at 18 hours is 24.9104 bacteria. Okay, now here's something I do want to point out. Decimal places. If you only put 2 decimal places, you're not earning full credit. There is the 0. I think they would give the credit there, so that's why I always encourage you to put 4 decimal places, just so that you can be safe. Now, we are gonna. So this is where we're gonna stop for today, because the bell is about to ring.